Okay, great. Why don't we go ahead and get started? So welcome back everybody to EE240. So not too much logistics-wise. I think we covered most of everything last time. Again, just I need to catch a flight, so I don't have any office hours immediately after this today, but certainly send me an email or just come grab me at some point if you have any questions or anything like that. On that note, how many of you guys have actually started homework number 3? One brave soul. Okay, so by the end of today, you should actually know how to do everything in that homework, and definitely go ahead and get started, because just as a reminder, that's due a week from today. And the midterm is basically another week after that. So you'll want to get going on that, because that stuff will definitely be on the midterm. Any kind of questions on material or anything like that so far, or should we just dive back in? Everybody's totally ready to go. You can tell me everything I need to know about gain-boosted cascodes, right? Okay, well, so I just wanted to kind of quickly review one thing that we had spent a reasonable amount of time talking about, and just to make sure sort of the context was clear. We talked about basically the overall response of the gain-boosted cascode in the frequency domain. And we said that that internal feedback loop was actually going to add these so-called pole zero doublets. And we said that that was going to sort of create some constraints on how we actually design that gain-boosting loop. So again, just to sort of make sure it's clear, I wanted to just kind of draw something really quickly to make sure everybody understood kind of what the context we're talking about was. So, no, it's not. Okay, hang on. Let's see. That's connected. Are you seeing it now? Okay. Okay, so sorry, brief technical interruption there. So last time, again, we were talking about gain-boosted cascode, and we were mostly talking about it in the context of current sources. So what we had basically said was that I would have a gain-boosted cascode that, let's say, looks something like this. Or obviously, we build our gain-boosting loop there with that extra amplifier, just tied to some VREF. Okay, but now what we were really mostly talking about in terms of what's going to set the overall response of that is actually if we were to use this thing, usually just a current source by itself is not particularly interesting, right? You'd actually probably use this in the context of an amplifier. So just as an example, I'm going to pretend that I built some current source on top, and that's, let's say, another gain-boosted cascode. And so now I'm actually going to use this thing as an amplifier. Okay, so kind of like we had been talking about, maybe I'll actually even use this in some sort of capacitive feedback configuration. Okay, so I've got some load cap that I'm driving. I have the output over there. Maybe I have some feedback, some capacitance over here, some input, right? So the real point here about that whole issue of the pole zero doublets, which just as a reminder, was really coming about because of the finite gain bandwidth of that gain boosting loop. The whole issue there is that if I've now tied this overall loop into closed loop feedback, then what's basically going to happen is I'm going to have sort of a couple of things that could be happening. So essentially, when I kind of drew this piece right here, conceptually what I really want is just some GM stage, right? And all I'm really trying to do is make the output resistance as large as I can possibly make it. Okay? So if I had some GM stage and, okay, we said we have it in some sort of feedback like this, and then driving some load capacitance, then what I'm kind of trying to do is get a gain bandwidth that's somehow proportional to GM divided by some effective load capacitance, right? That's kind of like the speed that I'm trying to operate that circuit at, right? Okay, so now the whole point there about that so-called pole zero doublet, which again, if you remember, you were going to get a pole zero doublet right at the gain bandwidth of that gain boosting loop. The whole point there is that if that pole zero doublet shows up at a frequency that's less than this gain bandwidth that you're actually trying to use the real circuit in, it'll basically mess up your settling response, right? If you remember, we said you'd get some curve that would look like, if this is, let's say, V out versus time, if this was the ideal input step, you get some curve that would maybe look like that, right? Now, again, I've exaggerated the effect, but basically this slower settling thing here, that's really coming about because of that pole coming from this internal loop here, where if that pole is slower than the gain bandwidth of our overall circuit, it's basically going to dominate our response. Okay, and again, just as kind of a reminder, anytime you have two poles, you can always do like partial fractions and then split that up into the time domain as well. So you're going to get one response that's some exponential settling, where the tau is just obviously 1 over omega p1, let's say, plus another exponential response, where that tau is 1 over omega p2. Right? And in this case, let's say omega p2 is from the gain boosting loop. If that pole is lower frequency than this thing over here, that's what's going to cause this extra slow tail at the end. Okay? Yeah?
How far do those pole and zero have to be apart for you to kind of notice?
Well, okay, so that's actually the interesting question. So basically, the distance between that pole and the zero in the frequency domain is actually also what's going to set this height right here. Okay? So the trick is that if you do it in the frequency domain, especially because you do it in a log, it's hard for you to tell usually. But if you do this in time, remember the whole reason I did this in the first place is because I wanted some fairly precise amplifier, right? In other words, I really wanted to make sure that the open loop gain was sufficiently high that I'm going to settle to within that certain accuracy within a given amount of time, right? Well, if you kind of think about it just intuitively, and by the way, you'll see this more in the homework from this week, what's basically happening is that if this thing is kind of slow, initially it's as if you don't have that feedback, right? When I first put that step in, if that step is sort of too fast relative to this feedback, then I essentially am just getting only the output resistance of the cascode, right? That means that if I bothered to add this thing in the first place, even though this may be some very small residual error, it actually matters, right? Because the only reason I would have added that in the first place was to try and fix that small residual error, okay? So, you know, there may be some weird situation you're in where, I don't know, maybe there's some other consideration that you had to actually do this, but 90x% of the time, if you actually built a circuit like this, that means you really cared about that last little piece of the settling there. And that means that you really want to make sure this gain bandwidth is greater than the gain bandwidth of your overall loop or your overall amplifier you're actually trying to build.
In which case you won't see that behavior at all.
Yeah, so I mean, it's still there. It's just that it's kind of masked out. In other words, this is so small that, you know, or really, yeah, in some sense it's basically being masked out by the fact that your overall settling, which is coming from now, you know, this, if that's actually slower than the other one, then it's as if like that, you know, this internal loop just settles first and you never really see it inside of it, right? Does this make sense to people, or? Okay, now just as a reminder, and again, you'll see this on your own homework. So this basically tells us that the gain bandwidth of the boosting thing in some way had better be greater than the gain bandwidth of our overall amplifier, right? But we also said that there was another constraint that was coming from stability. What was that constraint? What did that have to do with? Anybody remember? I have that little feedback loop inside of this thing that, you know, yeah, it has to do with the phase margin. And in particular, what was the other pole that you had to contend with inside of that gain boosting loop? No, the load we've actually sort of already taken into account here. There we go, the intermediate capacitance, right? Which, roughly speaking, we said was somehow related to the FT of that cascode transistor, okay? So keep those things in mind. Again, you know, if you've forgotten it or you know it's not quite clear, you'll be doing it in the homework, so it should be very clear by that point. Okay, so now, just one quick thing I wanted to mention is, you know, in our technology, and in fact most technologies you're probably going to work with these days, unfortunately the GMRO you can get from a transistor isn't all that great. Okay, so you can maybe get something like about a factor of 10 gain from sort of a short channel device. Okay, so if you cascode it, that goes up to, let's say, a factor of 100, And then let's say you do the gain boosting, maybe that goes up to about 1,000. But let's say you need a gain of like 10,000, right? What are you going to do then? Well, stacking yet another cascode on top of it is kind of painful, right? Because again, voltage headroom and things like that kind of get screwed up. Well, so there was a guy here at Berkeley, actually maybe about 5-6 years ago, who said, well, okay, so if I really need more gain and I don't want to pay for the extra headroom, why don't I take the amplifier that was inside of my gain boosting loop, and inside of that amplifier, build it as a gain boosted cascode, right? In other words, I'm just trying to up the gain of this amplifier inside of the gain boosting loop by gain boosting it as well, okay? So this is kind of like a recursive sort of thing in some way. Basically, you're nesting the gain boosting loops, right? So this works. It's a very nice, interesting technique. What's the sort of obvious pain in the butt here? Other than just designing all these different amplifiers. Yeah, I've got pole zero doublets up the wazoo, right? So if you were to do this, you have to be really, really careful to basically shove all those pole zero doublets out to a high enough frequency that they're not going to screw up your overall response. Okay, but indeed, this is something you can do, and I guess you could even get really aggressive and try and gain boost the gain boost of the gain boost, but obviously at some point this gets really painful to deal with. Okay? Bottom line is, if it works once, potentially you can actually do it again. Okay, so we spent a lot of time sort of talking about cascodes and gain boosting and things like that. So I finally wanted to just come back and talk a little bit about the implications of noise of all of these different techniques. Okay? So what I'm showing here is basically just 3 different current sources. So one is just your sort of standard single device current source. Over here I've got the cascode. And here this just looks a little bit funny, but essentially this is a gain boosted cascode. Right? I just built that gain boosting amplifier out of a common source stage. Okay, and there's no reference voltage explicitly. But basically this is just a gain boosted cascode over here. Okay, so now first question I want to ask you guys is, if I was to compare the noise of this simple current source, and by the way noise I mean the noise current obviously. So if I was to compare the noise current of this very simple current source over here with the noise current of this cascoded current source, how different do you guys think those are going to be? Or how much, I should say maybe, is this going to be better? Is this going to be worse? Like, is it going to be the same?
Same.
Okay, we have 1, 2 votes for same. Maybe we'll do it as a vote. So who thinks it's going to be worse? Better? Same? Okay, so why is it the same?
I think we did an analysis a couple lectures back, and the cascode doesn't add any noise.
Okay. Did you do that in the discussion session maybe, or?
I thought we did that in lecture.
Okay, possible. I don't think we did, but that's okay. So if that's the case, why doesn't it add any noise? So if I did do it, then you guys should know the answer. So why doesn't it add any noise? Why is it the same?
It's just the same current.
Maybe it does in
So
142.
the same current noise.
Not quite. So, I mean, you're sort of right. So, obviously, let's maybe walk through it, right? So, over here, I've got some noise current there, right? So now, if I'm going to measure, let's say, the noise voltage at the output that's caused by that noise current, what's the sort of loop that current has to flow through to get to the output? What sort of path does it take? And just to be explicit, I'll draw a little supply voltage over here. So what path does that noise current have to go through?
The channel of the MOSFET above it.
Okay, yeah, so it has to go up through here, right? Then it would go essentially through the output resistance. Some of it's in the capacitance, but that's fine. Back over here, and then come back, right? Okay, so now here's the interesting question. Let's assume that I have quote-unquote ideal devices. Okay, so when the transistors are in saturation, I magically get infinite R out. Okay? So basically, what I want to know is, for that noise current, how much of it is going to flow through that path that I sort of drew there in red? What percentage has to flow through that path? think I heard somebody say it. Just speak up, maybe. How much has to go through that path?
One thing.
Yeah, everything, right? There's no other place for it to go. So 100% of the noise current has to flow through that path. Okay, now here's the more interesting question. So if I take the cascode and I just erase that path, but remember, to get noise voltage at the output, you have to flow somehow into the output node. Okay? So now let me just draw like the small signal model of that cascode, right? So I have some GM Vs. And then from a noise standpoint, I'm going to have some noise current there. Right? So now, by the way, I'm pretty positive we didn't talk about this, so maybe that's not where I'm getting some answers, but that's okay. So I've got some noise current over there. So for that cascode, where's that noise current going to go? What loop is it going to flow through?
The same loop.
Actually, is it?
The cascode loop.
Yeah, it's got to flow inside of the cascode device, right? Because if I just look right there, looking sort of down out of the bottom of that current source, looking down, I have an infinite impedance, right? There's no way for me to flow any current through there. So my only choice is to flow up back through that GM. Well, guess what? And I'll draw it maybe in a different color just to be clear. Oops. Well, okay, that's fine. Noise current in that, noise current flowing in that loop never makes it to the output, right? Doesn't do squat to the output because, okay, fine, I wiggle around on that Vs over there, but who cares? That's totally isolated from the output, right? So now, obviously, we have real transistors, and so their RO is not infinite. And so some fraction of this current, and let me draw the RO. So some fraction of that current will actually flow through the RO of that bottom device, right? And of course, also, there's a finite RO over there. But basically, what will really happen is only some small fraction sort of flows back through that RO and then goes through that loop. And it's only that small fraction that would actually show up as being any noise at the output. Okay? So that's why, at least at DC, that cascode doesn't really have too much of an impact on the noise created by the current source. Okay? Now, does that work out to infinite frequency, or does something go wrong if we start going up to pretty high frequencies? What do you guys think? Maybe we'll do the easy question first. So who thinks something breaks just, based on my tone? Raise your hand. Okay, good. So now, what breaks? What's the problem with high frequencies?
CGS.
Yeah, okay, yeah, basically. So what about CGS? Or what about, let's just say there's some, let's call that CX. So what's wrong with CX? Why is that bad news?
It's going to short RO at high frequency.
Yeah, exactly. It's just going to short the RO, right? So at high frequencies, that noise current's perfectly happy to just flow right through that CX. And then all of it sort of shows up at the output, right? So if you guys remember, I had mentioned a while ago that, actually not a while ago, last time, that you want to keep this CX pretty small. Well, you want to keep that small, A, because that's sort of going to set up the stability of, let's say you did a gain boosting loop, or in fact, even if you just do a normal cascode, it's going to slow that, that basically the signal down. But perhaps even more importantly, if you don't make CX too small, actually you'll start picking up some of the extra noise coming from the cascode itself. Okay? So you're sort of doubly motivated to keep that CX pretty small. Okay, so if we've got that down, now we can go to the next interesting question. So now, for this gain boosting loop, let's repeat the same question. So, for the gain boosting, who thinks the noise for that gain boosting thing is going to be worse than the normal cascode? Raise your hand. Same? No brave souls. Better? Okay, well, at least we know it's not going to be better, right? So it's going to have to be either the same or worse. So what do you guys think? What's going to happen here?
Worse.
Okay, why worse?
Because you're getting gain, so it must be worse.
Okay, so I heard you're getting gain, so it must be worse. There was another thing over here somewhere. Say that again?
More capacitance at the intermediate node.
Ah, okay, you're actually a little bit clever. So you're saying that, well, hey, I added something on here, so of course there must be some CGS from that amplifier. That's going to add some cap there. I agree with that. Let's assume I can make that pretty small, and usually I can make that reasonably small. You're absolutely right, but I'm going to kind of claim I can make that a little bit small. Any other thoughts why it's worse? By the way, I didn't claim it. It is actually all that worse, so we'll see in a second what really happens. Any thoughts? So by the way, anytime you add a device that's doing something, what does that device have to also do?
Add noise.
Has to add noise. Okay, so if you did the sort of pedantic answer, you'd immediately say, okay, it's got to be worse, right? Because you added capacitance, because you're adding noise. That's all true. But now the real question is, how much worse is it? And in particular, let's ask the question this way. If I was looking at DC, and again, I had my perfect transistors, so the RO is really, really high. Is it really any worse? What do you guys think?
No.
Okay, no. Why not? What's going on? So, if I added some voltage noise over here, right, just right at the gate of that cascode device, what's that going to do sort of in terms of noise current for the cascode? What's it going to do?
Times GM.
Yeah, it's just going to get multiplied by GM. So I'm going to get some noise current showing up over there. That's basically GM times the noise voltage that got at the input, right?
Oh.
Is that noise current any different than the noise current of the cascode itself in terms of what loop it has to flow through? No, right? Nothing magic here. So in fact, at least, again, at DC, all that gain boosting loop does is, yeah, fine, it creates a little bit more noise current right here. But as long as my output resistance is reasonable, or really my GMRO is reasonable, then actually I'm not going to be adding all that much more noise in. Okay, because again, most of that noise will just flow inside of the cascode device by itself, right? Or to say it another way, if you like to think of it that way, you're sort of degenerating the GM of that cascode by the RO of the lower device, right? Which means that basically not all that much of its current is really making it to the output, okay? So in fact, in case you don't believe me, this is just showing sort of a quick simulation of those, actually 3 circuits comparing against each other. And in fact, I think 2 of them you can't even tell because the MOSFET and the cascode are sort of almost completely on top of each other. So that's kind of like the pink and the dotted line right there. And all that's showing here is basically this is the noise density. And this is like the total integrated noise you get across all frequencies. Okay? So what you can see is, the MOSFET by itself and the cascode, they're kind of right on top of each other. If you really zoomed in, you'd see a minor difference there. And you'll see for the gain boosting, okay, there's a little bit of extra integrated noise. And most of that's just coming from that region right there. Okay, and the only reason you're getting a little bit of extra noise there is that basically the gain bandwidth of that gain boosting loop is starting to run out at some point. And so you start picking up a little bit of the noise from that gain boosting loop. Okay, but on the net you can see this is a really small difference. I think it's like, I don't know, 20%, 15%, something like that. Okay, and in particular, down at lower frequencies, they're almost really exactly the same. Right, so it's really only up over here if you have a little bit of, running out of gain bandwidth that you sort of get a little bit of extra noise there. Okay? But bottom line, what's really nice about those techniques, or really what's nice about the gain boosting, is you can indeed actually get a higher RO, meaning you can get a higher DC gain, and it doesn't really impact your noise. which means that, in fact, from a power consumption standpoint, also there's, I should be able to get away with a pretty low power consumption inside of that extra gain boosting amplifier, which is really good news because, again, the only point of that was just to boost DC gain, right? And remember, if you're spending power, that should really be because you want to move some charge onto a capacitor quickly, right? Because after all, that's kind of the only reason you should be spending power, right, is just to move stuff around, okay? So these gain boosting loops, really what ends up sort of setting your design constraint there is more just meeting these constraints that we talked about here. So just making sure the gain bandwidth is high enough that you don't basically screw up the overall response. But since that thing is only driving the cascode and not like the bid load cap, usually that's not too expensive, okay? Does this make sense to everybody? Or? Okay, good. So just one last really quick thing that I want to talk a little bit about, which hopefully you guys have all seen before, is just, if I really was building a cascode current source, just, roughly speaking, how would you go about sizing that thing? Or kind of what sort of design decisions would you be making about, let's say, the V star and the channel length? Okay, so again, let's say that's my cascode, and this is my current source. So what do you guys think? How, what are sort of the choices that you would make in terms of building these things up? And let's start out maybe with that bottom device, M1. So what do you want to do for M1 if you're building a current source? How do you usually want to size that thing? And I don't mean numbers, obviously, like qualitatively.
Large RO.
Okay, large RO. What does that usually imply?
Bigger L.
Yeah, basically, you typically want a long L over here, right? Just to get a good RO. Anything else, particularly from a noise standpoint, that we had talked about? Like, what kind of V star do you want to use? Well, okay, no, I didn't mean the number. I meant like, you want a big V star or a small V star, relatively speaking.
Always want
Big V star.
Yeah, to the extent that you can, you kind of want a large V star, right? Just because getting GM out of that transistor only causes you noise. Now, again, there's the whole discussion we had about swing versus noise, but if you, at least if you, all you cared about was just you reducing noise, then you'd want sort of a large V star, right? And in fact, even if you care about SNR, you kind of want to make that kind of as large as reasonable to make it, okay? All right, how about this top device over here? How do you think you're going to want to size that? Let's start out maybe with the channel length. What kind of channel length do you think you want? Long, short, medium? What do you guys think?
Short.
Short, okay. Why do you say short? I agree with that, by the way, but why do you say that now? What's good about a short channel length device?
Faster.
Okay, it's faster. What does that kind of, specifically, how does that help me in this context? I'll give you guys a hint. What do we want that CX that I just drew to be? Yeah, we want that thing to be small, right? So if I use a short channel cascode, okay, granted, I'm always going to have the drain cap from the long channel current source, but at least I'm not going to add too much to that, right? All right, actually, that sort of touches on another thing. So what do I want to do with the V star of that device? Want big, medium, small? What do you guys think?
Small.
Okay, I tend to agree with that too. You probably want a reasonably small V star there, right? Because if I'm using a short channel length, I can get actually pretty high FT, even if I use a reasonably small V star, let's say 150, 200 millivolts, something like that, or maybe even 100 if I'm really aggressive. And because I'm using a short channel length, again, I can kind of get the FT out of it, right? Now, obviously, all of these things are kind of generalities, so you'd have to really look at the exact thing that you're building. But oftentimes, this is a typical sizing that you would see, right? So you'd have a long channel current source, and then a short channel cascode sitting on top of it. Right? And by the way, just as a reminder, using a small V star here, again, really doesn't hurt you all that much from a noise standpoint, because, again, most of that current is just going to flow internally in the transistor. Right? It's not actually going to show up at the output. And in fact, if we get sort of more GM per unit current, that's in some sense good news, because that means more of the actual current you want is really going to make it to the output. Right? So fairly typical sizing that you might see there. And in fact, there's another sort of benefit here, which you'll see more later on when we really get into sort of doing some high-speed stuff. The other nice thing about this is now, since I can size the cascode device independently of that long channel current source, it lets me get not only high output resistance at DC, but because I can make that drain cap from the cascode smaller than the drain cap I would have gotten from the long channel current source, that can actually also help me increase the output impedance at high frequency as well. Right? Because at high frequency, higher output impedance just means smaller cap. Okay? So this is, again, just sort of, I'm not giving you any numbers here, because obviously it really depends on what exactly you're doing. But this is just to kind of give you an idea of what some of the design trade-offs are and where that you usually end up being pushed in terms of playing around with the sizes of these devices. So any last questions on this before we move on? Or you guys are all hotshot cascode amplifier or cascode current source designers now? Yeah?
How does small V star help us again? In terms
So
of the cast?
the small V star sort of helps in a couple of ways, right? So one is, remember the gain you get is, or the RO you get is going to be RO of this times the GMRO of that, right? So if I use a small V star here, that means I can tolerate less voltage across there and still get a relatively high GMRO, right? It also, well, really not the small V star, but the short channel length is helpful because that means that, again, the parasitic capacitance you're introducing potentially is small. Now, obviously, these two trade off with each other, right? So if you had a really short channel length but a ridiculously small V star, then that may not make sense. That's why I kind of put these things in quotes. But this is a typical sort of reasonable spot for you to land in, right? Because by changing that V star, you can get better sort of swing across the whole structure and not pay a whole lot from a parasitic capacitance standpoint. Okay? It also helps just because, again, remember, you've got some current coming out of the bottom transistor over here, right? The real transconductance. You want all of that current to flow up through the cascode, right? And the smaller the 1 over GM, the smaller the 1 over GM, meaning the larger the GM is, the more you're going to make sure that current really flows up in that direction, right? And remember, the bias current through this whole thing, it's fixed for both of them. So in some sense, the only way you can sort of play games with the relative GMs is by changing the channel lengths and changing the V stars. Any last questions on this? Or? Okay, so if not, let's go ahead and actually move on to the next set of slides here. Okay. So now that we sort of talked about current sources, we've already said a few times now, obviously current sources are nice, but you actually want to use that to do something. So of course, probably the first thing you want to do is build an amplifier. So let's just take a look at that. And in particular here, usually when you sort of first learned about amplifiers, you kind of learned about operational amplifiers, right? Probably back when you took your first circuits class, or maybe even your intro to EE class, everything was all about operational amplifiers, right? Well, so what we're going to talk about today is, okay, op amps are nice, but turns out for most of what we're going to be doing, you actually don't really want to build op amps. What you really want to build is what's called an OTA, or an operational transconductance amplifier. So to see why that is, we can kind of just think about the characteristics of an op amp, okay? So in an op amp, obviously what you want is high, ideally infinite voltage gain, ideally infinite input impedance, But really the thing that's sort of a little bit funny, especially if you're a MOSFET designer, is that when we draw this symbol like this, we also assume that the output impedance is 0, meaning that we have a voltage source over here. So that this whole thing is basically a voltage-controlled voltage source. Well, so if I start just thinking about, okay, I want to build this out of MOSFETs, and I just, let's say, build the simplest, common source amplifier I can, well, right away I sort of see that something doesn't sort of quite add up, right? Or something doesn't quite match up, I should say, right? Because if I look into that output right there, the RO ideally should be infinite, right? Which is exactly the opposite of a voltage source. That looks more like a current source, right? So really in sort of MOS-based circuits, and actually almost every semiconductor circuit that I know of, most of the time what you really want to work with is OTAs, or again, operational transconductance amplifiers. So again, the only real difference is here, basically, you still want ideally infinite gain. You still want high input impedance. But now for an OTA, the output impedance is infinite, meaning it's a current source driving the output. Now, I should just mention one other thing here, which is that, when I say that this thing has high quote-unquote voltage gain, obviously I'm being a little bit fast and loose with the units, right? Because my gain here is really a transconductance, meaning per unit voltage at the input, how much current do you get, okay? But other than that, it sort of looks the same. It's just that this thing, that I can build pretty naturally, right? And in fact, as we'll see in a second, in fact, not only does it naturally match up with what we can actually do, in many cases, we're actually going to prefer to do this over this, okay? And we'll see why that is in just a couple of slides. So first, let's just, obviously if I have some op-amp or OTA, and in particular, let's say an OTA, and somehow I really get that magic ideal, meaning I have infinite gain, well, usually infinite gain in and of itself is not, well, I shouldn't say it's not useful, but it's sort of hard to use. So usually we have to tie that in feedback, right? So let's just look at what happens if we tied an OTA into feedback. And let's, by the way, compare that to what happens when I tie an op-amp into feedback. So in an op-amp, if let's say I was to tie the feedback loop like this, well, I've got a voltage source output over here, right? So that voltage source can drive any load resistance you want, and it'll still have infinite gain, right? So if I was to break this loop, let's say right there, I would always have infinite loop gain, right? No matter what the feedback resistors were. Well, now if I try and do this same thing with an OTA, again, remember, my model for an OTA is just a GM over here, GM times Vn, let's say, right? So now, unfortunately, if I was actually to break that loop, and let's say, I just ground this input to look at sort of just the open loop transfer function, now what I basically have is GM driving the loaded resistance from those feedback things, right? That's kind of bad news, right? Because basically now, depending upon what, let's say RF and RS I use, my open loop gain is actually going to change, right? So I'm actually loading my OTA. Well, that kind of sucks. So, okay, I could try and fix this. I could say maybe, okay, fine. Maybe I use like a really, really big feedback resistance. All right, so maybe I use like mega ohm or 10 mega ohms or something like that, just so that it doesn't actually load my amplifier. Well, okay, maybe I could do it, but again, that sounds like bad news, right? Because those resistors are probably really big. They also are going to introduce lots of parasitic capacitors. They're going to slow my amplifier down. And in fact, there was even one more thing we said that was really bad about big feedback resistors. Anybody remember that? Yeah, they had a bunch of noise, right? So it's kind of like triple whammy. It's big, it's going to slow you down, and it adds noise into the system, right? So it doesn't sound like a very attractive solution. So we're going to need to do something else. Well, as you can probably guess, since we've talked about it like 3 or 4 times already, what you're instead going to actually do, if you have an OTA, is use capacitors for your feedback. Okay? So the way these things work is actually, or conceptually, it's very, very similar to the resistive feedback. Right? Because really all you're trying to do is create a voltage division between V out and Vx. Okay? Well, what's nice about capacitors is that now, at least at DC, right, this is infinite impedance, right? So it's not going to be loading my OTA. So I'm still going to get sort of the ideal open loop, let's say, quote-unquote, infinite gain I used to have. And I can still choose different sizes for these capacitors without actually messing up my feedback transfer function. Okay? Now, that's not to say that capacitors are sort of perfect, right? Obviously, at higher frequencies, the impedance of these is going to get lower and basically slow your loop down. But of course, that was going to happen anyways, right? Any circuit has capacitance in it, and there was always going to be some feedback, or excuse me, some bandwidth limit because of those capacitors. Okay? Even in an op-amp, obviously the op-amp has a finite output impedance, and eventually you're going to run out of speed there too, because of the capacitors basically dropping in impedance. Okay? So at least we've solved this problem now, right? I can build an OTA, or at least in principle, that still has the same sort of feedback gain that I had before, and I don't have to worry about that feedback network loading the amplifier, at least at DC. Okay? But so now the question is, of course, does this really actually work? And so to turn it around back to you guys, if you were to take this circuit and plug it into HSpice and just hit the button and simulate it, what would HSpice say to you? If you open the error log, what would it say? Yeah, there we go. Right? It'd say no DC path to ground at node Vx. Right? Convergence failure, simulation aborted or something like that. Right? So why is that a problem? Why is it that Spice is complaining, and in fact, if you as a circuit designer, somehow you magically got Spice to simulate it, why would you be worried about something like that? What does that mean? Yeah, it turns out it's actually not quite an integrator. I'll explain why that is in a second, or I'll explain how we would make it not exactly be an integrator, but you're exactly right about the other thing. Right? Basically, you don't know whether this Vx is really going to sit at DC. So if there's any, small little, I don't know, 1 femtoamp, leakage path into that thing, if you run the thing long enough, eventually that voltage will go up to some ridiculous point where obviously the whole circuit doesn't even work anymore. Right? So let's say eventually this went up to like, I don't know, 10 volts or something like that. And obviously you've got only a 1 volt power supply. Well, nothing's going to happen, right? Thing's not going to work, right? And there's nothing that the circuit can do to fix it, because at DC, there's nothing really setting that bias point. Okay? So conceptually okay, but we're going to have to do something to sort of fix this up. So now, again, if you ran into this problem, what would you do to try and fix this? What's like the first most obvious thing you could do to try and fix this problem?
Put a switch in there.
Okay, put a switch in, but maybe since you seem to know this, I'll ask somebody else. What would you do with that switch?
Bias.
Bias. Okay, what do you mean by bias? I agree, but what do you mean?
At a voltage that we know.
Okay, there you go. Basically what you're saying is, why don't we just reset this thing into a known state? Right? Why don't we just shove some voltage onto there that we know is a good voltage? Okay? Well, I buy that. In fact, that's exactly what we're going to have to do. Right? We're somehow going to have to reset the charge across this capacitor, and of course this one as well, to some known state, so that we know we're not just drifted off into some bizarre place. Okay? Well, so the question I have here is, of course, well, okay, fine. So I have this initial problem, so how about I just put that little switch in there, and then when I start the circuit, I initialize things, and then I let the thing go, and I just run for some long period of time without ever worrying about it again. Well, it sounds a little bit scary, right? Because if I run the thing long enough, Even though maybe I reset it, I don't know, a second ago, 10 seconds ago, a minute ago, eventually it's entirely possible that the thing will drift off somewhere again that I didn't want it to be, right? So that kind of says that, okay, now what I really think I need to do is reset this on a sort of periodic basis, okay? So I'm actually going to claim that once you've done that, once you've sort of bought into the fact you have to reset this thing on a fairly periodic basis, what you're probably really going to want to do is actually reset it every single clock cycle. And by every clock cycle, I mean essentially every time you actually use the output. So now I just sort of made this somewhat bold statement. Anybody have an idea? Why do I say that? Why wouldn't I be okay with just, let's say, resetting the thing once every 100 cycles or something like that? Or 1,000 cycles, or 10,000, or 10, or whatever. What's kind of the issue you run into if you do that reset, let's say, once every 10 cycles?
Gain could fluctuate.
Okay, you're saying basically the gain could fluctuate. And by the way, what do you mean by that?
The output could go up, down every 10 cycles.
Okay, you're kind of going in the right direction. So, by the way, anybody know if this was like just a CMOS transistor? Can I basically do something like this? When I shut that transistor off, what's going to happen?
It's gonna leak.
It's going to leak, yeah. Is there anything else? And I'll give you maybe a little bit of a hint.
Charge injection?
Yeah, there's charge injection, meaning there's, actually we'll talk more about it later on, but there was some charge stored inside of there. When you turn the thing off, that has to go somewhere. Not only that, you're going to get some just coupling through the CGD, right? So bottom line, kind of like you were both getting at, if I just did this once every, let's say, 10 cycles, on that 10th cycle, when I actually do this reset, I'm going to get some glitches or weirdness at the output, right? So as an example, let's say that, I don't know, this was my input or whatever, and this was my clock, and then this is my reset thing. Then if I look at the output, let's say the output was nicely tracking, but then it got reset and so it has a little glitch on it. Right, and then again, it resets and has a little glitch on it. Okay? So by the way, especially if you were, let's say, doing something like an ADC or, I don't know, something else where you want to measure a really precise signal, or maybe even actually even better, if you wanted to measure like some, you're doing an RF front end. What's really bad about those glitches? What are they going to cause in your output?
Sure is 10.
Yeah, they're going to cause spurs, right? Because basically every 10th cycle, some weird phenomenon happens, and it's showing up kind of independent of your input, right? Which basically means that there's sort of this extra energy sitting there at that particular frequency, right? And again, especially if you're doing something like an RF receiver or an ADC or something like that, where you really want to know what was the actual input, it's really bad when clocks that are just from your measurement circuit show up as being what you're actually measuring. Okay? So that's why I claim that if you're going to do this, you should actually do the reset every single cycle. And again, by every single cycle, I mean every time you use the output. Now, by the way, why is it that if I do this every time I use the output, why does that make this particular problem go away? Any thoughts?
Predictable.
You're going in the right direction, actually. You said it's predictable. Anybody else want to follow up on that?
Taking the measurement right after that happens.
Okay. That's also true, but so what else is actually true about this? So let's say that I did this every single time. Okay, so I have those little glitches on every single little clock cycle there, right? But then all I do is I look at the samples right at those times. Kind of from this picture here, what does it look like the glitch is actually doing?
Shifty.
Yeah, it's just shifting it at DC, right? So in some sense, if I'm using that sample every single time, even if that glitch or that turning off that switch creates some badness, at least it's the same badness every single time, right? That's much, much easier to deal with. Right? As an example, I could just build something afterwards that looks at that output and tries to cancel that badness, right? Because it's always the same. So every single sample is corrupted the same way, and then at the very least, I won't get like, some spurious tone out at some weird frequency. I've got it at DC, but that's a lot easier to deal with. Okay? So name of the game is now really going to be, if we want to do this sort of capacitive feedback, since we're going to have to reset things every cycle, what that generally ends up looking like is these so-called switched capacitor circuits, or in this case, a switched capacitor gain stage. Okay, so I've kind of drawn an example of one of these types of switched capacitor circuits here. There's a bazillion different versions you can use. I'm not going to bother going through all of them because they all sort of work on roughly the same principle. So I'll go through this one in a little bit more detail in a second. But the basic idea in all of these circuits is in one of the clock phases, you're basically resetting everything. And then in the other clock phase, that's where you actually get a valid output. Okay? So again, lots and lots of different ways this can be done. I'm just showing one example here. We'll walk through this thing in 1 second. But really, all that all these switches are doing is either resetting the capacitors to some known voltage, or configuring the circuit into a way where you basically take that known voltage or take the input and amplify it in some way. Okay? So before I kind of walk through the details of this particular circuit, there's one thing that I do need to note here, though. So this phi 1 and that phi 2, that's like two different clock phases. Okay, so typical way something like this might look is if, let's say, that's phi 1, then this might be phi 2. Okay? And you'll notice here I intentionally separated the times from when they're supposed to be high. Okay? So that's what's called non-overlapping clocks. So by the way, anybody know why do I want to make sure these are non-overlapping clocks? What would be really bad if they actually, as an example, and maybe I'll draw it in red, what would be really bad if, let's say, something like that happened, where phi 1 and phi 2 were on at the same time?
Feed to ground.
Feed through. Okay, yeah, you're right, but let's pick off like one of the worst possible things that could have happened.
Source can get shorted.
Yeah, okay, so I could short out the source, right? That's kind of bad news. I could also be shorting out the capacitor so that I just have zero, I'm taking whatever charge I used to put there and basically eliminating it, right? But basically, if I have phi 1 and phi 2 on at the same time, bad things will happen in the circuit, right? It won't work the way you want it to, okay? So if you want to make sure that the circuit works, you always have to add this little non-overlap time in, okay? So that's all fine. That makes sure the thing works. But why do I claim that non-overlap time is kind of bad news still? Like, what's bad about that? Why is it that I don't really want to have non-overlap time there? Any thoughts? Let me maybe just give you some specific numbers. Let's say that I tell you, if you want to be safe, you have to make that 1 nanosecond. That's not a real number, but let's just say I told you that was my minimum non-overlap time. What does that tell you?
Slow.
Yeah, it's going to slow me down, right? Because basically during that non-overlap time, nothing is happening. Right? If you actually look at these with all the switches off, you can see nothing's actually happening, right? So although I need that non-overlap time to make sure the circuit actually works, it's just kind of an overhead, right? So as an example, if I wanted to run at, 500 megahertz, actually I couldn't even do that if I had a 1 nanosecond non-overlap, right? Because basically all of my time would just be spent in the non-overlap periods. So to have these, incredibly narrow little clock pulses, right? Which obviously not really going to work. Okay, so if you really were to build one of these things, you basically want to set that non-overlap time to be large enough that you're confident that the switches won't ever be on at the same time, but no larger than that, right? Because any larger than that, and really you're just taking away from your own time to actually do something useful. Okay, and that's actually going to cost you extra power. Okay? Does this make sense to everybody? Or? Okay, good. So let's actually take that particular switch capacitor gain stage that I had drawn there. And all I've done now is I've gotten rid of all the switches. but I'm just showing what happens in the two different clock phases. Okay? So this first phase, that's when phi 1 is high. And again, if you walk through that diagram that I had with the switches there, you'll see that, this is what the circuit looks like. Okay? So really all that I'm doing in this first phase is essentially just resetting everything to a known voltage. Okay? So over here at the input, what I'm literally doing is just sampling V in onto that input capacitor CS. Okay? For the output, what I'm going to do here is I'm just resetting this intermediate node also to ground. By the way, that might not really be ground. It may be some other voltage. We'll talk some more about that in a second. And in fact, if you pay sort of close attention, you'll notice I'm also even actually resetting the output to ground. Okay? Now, I sort of put this thing here in a slightly different color for a reason. So, if I told you that I was actually doing this with an op amp and not an OTA, so my circuit looked something like, something like that. And I told you I was going to say, okay, fine, now I'm going to ground that thing right there. Who thinks that's a good idea? Really bad idea? Why really bad?
Shorted the ground.
Yeah, right? That op amp is just a voltage source, right? So if I short that thing to ground, and by the way, again, ground may not be ground, it may be some other voltage. All I've done is I've literally taken two voltage sources and shorted them together, which usually results in, nice sparks and things melting and all kinds of other fun stuff like that. I mean, not really necessarily, but if you cared at all about power, you really don't want a whole bunch of DC bias current flowing from your op amp for no good reason, right? Okay, so for op amps, it doesn't sound like this is something you really want to do. How about for an OTA? Just sort of okay or not okay? What do you guys think? Will says okay. Anybody else?
High output impedance, so doesn't really matter.
Yeah, that's actually a good way of saying it, right? Basically, in the worst case, which we probably don't even want to have that happen, but in the worst case, I'll just have whatever the bias current of that OTA is flowing into that voltage source, right? And in fact, if I'm a little bit clever, let's say that my OTA actually looked, let's say something like that. Then if I just shorted this thing to, let's say, VDD, right? Then actually I'd have no bias current flowing at all, right? Because I would have grounded the gate of the NMOS device there. And if I pull the other side up to VDD, then basically I'm not actually doing anything bad, right? I should have actually no bias current flowing. Okay, and in fact I could even potentially tie that to some other voltage. And again, in the worst case, all that would happen is the bias current would flow through there. Okay, so that's, you obviously you want to be careful that you're not just burning a bunch of extra current when you don't need to be. But because it's an OTA, that's kind of, it's an okay thing to do. Okay? By the way, anybody know why I explicitly wanted to reset this output over here? To make it 0? Rather than just, if I didn't have that there, just let it be whatever it was? Any thoughts?
Just give it some known value.
Okay. How does that, what does that do?
You yank the left side of CF down, you're going to yank the right side of CF.
Okay, that's actually true, right? So when I yank this side down, I'm going to do something over here. That's, that could potentially actually be a problem, but in fact, there's even sort of a simpler thing to think about here. So usually when we told you that, I had an op amp with something, let's say a capacitor and feedback, usually what were you told that the function of that circuit was?
Integrator.
Yeah, usually you're told this was an integrator, right? But I don't necessarily want an integrator. What I want is a gain stage, right? Well, if I'm going to reset that output to quote-unquote ground every time, it doesn't matter what all the previous things that I did were. I'm just going to reset to the same spot every time. If I do this, I really do have a gain stage, right? Because remember, an integrator remembers all previous things that you did to it. Here, every single cycle, I get rid of all the previous history. right? So it really is just the gain stage now. Okay, well, so if we understand this, then actually, understanding sort of the rest of the operation is pretty straightforward. So, again, in phase one, all I really do is sample V in onto that capacitor right there. Okay, was there a question? Or?
Reason to like short the two ends of the CF to ground rather than just shorting across?
Oh, you mean rather than doing
Yeah.
this? You could do something like that. So if you did something like that, you'll definitely be burning sort of the bias current of the OTA during that time, but that's probably okay. So if you did something like that, then you're sort of just setting the OTA into its, let's say, DC nominal bias point. That's also basically okay. You could do that. That's fine. There's a little bit of a difference, and again, we'll talk more about this later, but if you do it this way, meaning actually explicitly shorting into a voltage source, versus just having that bridge switch there is a big difference from a charge injection standpoint. Okay, and again, if that's not clear now, come bug me. We'll actually be talking about that a whole lot more later on down the road. Does that make sense? Or? Okay. Okay, so just getting back to how this thing actually works. So in this first phase, we've sampled V in onto that CS. Then in the second phase, I'm going to tie this side to ground, and I'm going to connect that feedback switch. Okay? So now, somebody other than Dan, and I guess Will too, just by association. So if that thing used to be at VI, and I'm going to yank it down to 0, what's going to happen on this side over here, which, by the way, used to be at 0? Yeah, basically, if there was no other anything else in the system, it has to jump down to minus VI, right? Because you can't instantly change the voltage across the cap. Okay? But really, what's important there is to say that, okay, that basically means that if I look at the charge that was stored there, that charge is just going to be CS times VI. And just to be pedantic about it, I'll say that the magnitude of the charge, because it actually does have a sign associated with it. Okay? Okay, so now, if I have CS times VI of charge, and we just said that when I sort of close those switches initially, that's going to try and cause this thing to jump down to minus VI. What's the amplifier going to do to try and fix that? Or how's the amplifier going to respond to this?
Settle.
Okay, it's going to settle. What is it going to try and enforce? Like, where is it eventually going to stop? What do we usually call this node right here?
Virtual ground.
Yeah, it's a virtual ground, right? If that's a virtual ground, then the OTA is just going to basically start pumping some current into this output until that virtual ground comes back up to be really ground, right? Okay, well, so I claim that actually this is really easy to figure out, because we know how much charge got dumped onto that node. Right? So if we want to yank that node back up to where it used to be, all we have to do is supply that same amount of charge at the output, right? Which again is just going to come through there. Okay, so if I'm going to take basically CS times VI of charge to bring that thing back up to ground, what does that mean the voltage gain of this amplifier is? By the way, who remembers the relationship between charge and voltage on capacitors? Take that as everybody. Yes. Okay. So what is that?
Q equals CV.
There we go. Q equals CV. Okay. So we just said that Q is CS times VI, right? Okay. How about what's the capacitance that we're dumping that charge onto if we want to look at the output voltage?
CF.
CF, right? So that means that this should be equal to CF times V out, right? Because remember, I know that eventually that node is just going to go to ground. So the charge across that CF is just V out minus ground, which is of course 0. Okay, so now what's my voltage gain? What's V out divided by V in?
CS over CF.
There we go, CS over CF, right? That's exactly right. And of course, you could have seen the same exact thing if you just pretended, you drew those as boxes as being impedance, and you said the impedance was 1 over C, you'd get the same answer, right? Because it's kind of like the resistor case was, just because it's 1 over, you have CS over CF, rather than the other way around. Okay? Now, by the way, I didn't actually get the sign incorrect here. It really is positive CS over CF, even though we're tied to the negative terminal there. And the way that happened is just, notice in this first phase, I sampled VI onto the negative terminal. And then in the second phase, I basically connected the positive terminal to the negative over here. In other words, by flipping the switches across these two phases, I've basically inverted that input voltage. Right, or to say it another way, I caused this to go to negative VI. Okay? Does this make sense to everybody? Or? So, just to make sure it's really clear, if I sort of took that circuit and I used it in some, to basically amplify some waveform, let's just kind of quickly draw what that would look like. Okay, so let's say this is my clock, like this. Okay, and let's say that this is my input voltage, and let's pretend that I set this whole thing up to have a gain of 1, just to make my life easier with the drawing. Okay, so let's say I have something that's doing, I don't know, like that. Okay? Where this is, let's say, 0 volts right there. Okay, well, so, and let's assume that phi 2 is basically high when clock is low. So actually, I'll be more specific. This is phi 1, really. Okay? So remember, during phi 1, I'm just going to reset the output to ground, right? Then during phi 2, that's when I sample the input and essentially amplify it at the output. Okay? So if I was to track this waveform, then basically, right over here, of course slightly after that to get the non-overlap, that's when I'd sample the input. And my amplifier would just, well actually I drew it sort of as ideal, but obviously take some time for the amplifier to supply that current. So it'd have some settling, and then it just basically stays at that level right there. Okay? Then once phi 1 turns back on again, of course I reset the output. So I have something that, let's say, looks like this. Okay? Then again on the next clock edge right there, I actually sample the input, which is right there, of course. And so I'll slowly settle up to get to right there. Right, let's say I do something like this. Then again, I reset. So I go back to 0. Again, I sample. Something like that, and so on and so forth. Okay? Now, I actually was a little bit sort of aggressive in how I drew these things. Because again, this is actually going to take some actual amount of time. Right? Because that's just related to the amplifier. Remember, in that phase, the amplifier just sort of looks like that. Okay? So during that time, it's basically just, you put that glitch on the input right there. And then it's just going to settle with whatever the dynamics of that feedback loop are to get up to that final value. Okay? And if you've done things well, which, now that you're in 240, hopefully you will, basically that should look a lot like sort of a single pole settling, right? It's just going to be GM over CL effective that sets the pole, and that's what would set that time constant right there, right? So now actually we're going to talk a whole lot more about settling in maybe about a week or so, actually maybe 2 weeks. But basically, this is already kind of telling you, just by knowing that this is how the amplifier is operating, you can already pretty quickly figure out how you're going to want to choose that GM over CL based on how fast you're operating, right? Because obviously if I make this clock period shorter, I better make sure that my amplifier settles fast enough so that I actually really get the value I wanted at the end of that clock period. right? Because if I don't, then actually, I'm still going to be moving around and I won't really get the value I wanted. Okay? So again, we'll talk a whole lot more about that, but this is really just to make sure that it's sort of clear how these amplifiers are operating. Okay? So remember, even though my output is 0 at all these intermediate points, that doesn't matter because I'm not really using it then. That's just during the reset. I really use it kind of at the end of these clock periods. Okay? Any questions on this, or? Okay. So now I claim we're actually in good shape to go back, and I'll justify my original claim about why is it that you actually, in fact, don't want to use op amps in many of these situations. So to see that, I just want to sort of show how you might actually build an op amp, and not exactly, but similar, or roughly speaking. So let's say you really wanted to build an op amp. So what you could basically do is, you know that you sort of have almost all the characteristics you need from an OTA. Right? Because you have infinite input impedance, you have infinite gain. You just don't have that low output impedance. Well, so how would you do that? Essentially, you could take your OTA, which let's say was just a common source amplifier, and then add to its output a buffer, otherwise known as a source follower. Right? So now if I do that, I kind of can claim that I have an op amp. Because as long as that 1 over GM looking into that is sort of small enough, now it really looks like a voltage source output. So in fact, for exactly this reason, that's why if you look at the symbol of an OTA versus an op amp, the OTA is essentially just an op amp with its head cut off. Right? Because that head, that's like the buffer. This is the OTA. Okay? So now keep in mind, when you actually build these things, that really means you have an OTA followed by a buffer. So I'm going to claim for this reason, in fact, if you looked at like switch capacitor circuits, if you used an op amp, you're actually going to end up burning more power, and your performance is going to be worse. Okay, so let's see how that happens. So to see that, what I'm basically going to do is say, keeping in mind that really this is what the two things look like, let's see what would happen if we took an op amp and tied it into unity gain feedback to drive some capacitive load, versus an OTA and tied it in unity gain feedback to drive a capacitive load. Okay? Well, and so what I want to sort of characterize here is how much noise would those two things have? So I'm going to make this OTA and that OTA, I'm going to make those completely identical. Okay? And in fact, I'm even going to be generous. I'm going to say that this buffer doesn't even add any noise at all. And if you did homework number 2, maybe that's not exactly right, but actually you could sort of argue why maybe it won't add all that much noise. Okay? So let's just take a look at what sort of the equivalent circuit I have here from the standpoint of calculating the noise. So if I look at the OTA, when I tie it into feedback like this, like we've seen many times already, that's kind of like just taking a transistor and putting it into a diode connection, right? So that's kind of like saying that the output resistance of this is 1 over GM. And if you remember when we input refer the noise voltage, the noise current to be a voltage, it just becomes 4 kT over GM, right? Okay, so if I take this circuit, I can very quickly say, okay, fine. I have a noise voltage that's 4 kT over GM, and I have an output resistance that's 1 over GM. Well, guess what? That's exactly like just having our, good old RC circuit that we calculated way back in the beginning, right? So the noise for this will just be KT over CL. Because the thing that, the effective resistance that creates the noise and the effective resistance that set the bandwidth are exactly the same, right? Now, if we actually look at over here with the op amp, now our life is actually kind of not so good. Because, okay, noise voltage, again, I'm only going to include the noise from this OTA, didn't change, right? That's still just going to be input referred, 4 kT over GM. But now, if I look at the output resistance of this thing, it's not 1 over GM anymore, right? I intentionally added this buffer just to lower that output resistance. So whatever that output resistance is, let's just call that RS. That's what's actually going to set my bandwidth, right? So now if I again sort of repeat all, these simple integrals, what I'm going to get is, this is the noise current, the noise voltage density. This is the integration of that transfer function. And so if you look at it, I'll still get KT over CL, but unfortunately I'll get Rn, which here I've just defined Rn as being 1 over GM over Rs, right? And remember, the whole point of adding this thing in was that you wanted to make sure that Rs is actually less than 1 over GM, right? Because that's how you get lower output impedance. So now this is bad news, right? Because notice we just said that we're guaranteed that Rn over Rs is greater than 1. Well, this seems like really, really bad, right? Because I added that buffer in to get lower output impedance. So I'm burning more power than I used to be. In fact, I might even be burning a lot more power than I used to be. And then I take it and I kind of use it the same way I was before. And all of a sudden I have, let's say that output impedance was 5 times lower. Now I've got 5 times more noise, right? And again, this just sort of makes sense, right? Because if I did this, I'm just expanding the bandwidth, right? I expanded the bandwidth by a factor of 5. And so that's exactly how much extra noise I'm going to get. So in fact, if you go back and you dig up into the literature, when people first invented switched capacitor circuits, they unfortunately didn't think about this too carefully. And they actually used op-amps in their switched capacitor circuits. And then again, if you actually look at some of the literature, people say, oh, switched capacitor circuits are horrible. They'll never be better than continuous time because they alias noise from all kinds of different frequencies and they have worse than KT over C. Well, it turns out it just had to do with the fact that they were using op-amps and not OTAs. In other words, they were making the bandwidth intentionally much, much wider than it really needed to be. Okay? So from that standpoint, again, in most, a lot of the context that we're going to be doing things, that's why we can actually safely claim that you'd actually prefer to use an OTA versus an op-amp. Okay? Now, there are some places where you really need to drive not capacitors, but resistors. Okay? As an example, let's say something that was, talking between 2 different chips or driving a power amplifier. There, you have to drive a resistive load. In that context, now it makes sense to actually have an op-amp. Because if you didn't, then the resistor really does load the OTA. But for a lot of the stuff that we're going to talk about, which is sort of on the chip, OTAs work just beautifully fine and, in fact, are really what you want to do. Okay? Does this make sense to everybody? Or? All right, so just one last quick thing before we wrap up for today. Since this is on your homework, I just wanted to sort of make sure that it's clear to everybody. All right, so if I have one of these switched capacitor gain stages, I claim actually you basically know everything you need to know in order to calculate the noise. But there's just one thing that usually confuses people initially. Okay? So let's just go in and draw, our switched capacitor amplifier in the first phase of operation. Okay, so during that first phase of operation, I'm just tying everything on the op-amp itself to ground. And I'll explicitly draw the switch here just so that it's clear. And I'm basically sampling that input voltage. Okay? So now, right when phi 1 basically goes low and turns that switch off, am I going to have any noise here or sampled onto that capacitor or no? What do you guys think? Yeah, I'm going to sample some noise onto that capacitor, right? By the way, where's that noise actually coming from? Yeah, from whatever's actually driving this thing. Because in particular, especially if I'm doing switch capacitors, what's probably the case is that I'm being driven by the previous switch cap stage. And you can imagine if you're going to do one switch cap stage driving another switch cap stage, you basically sort of ping pong them, meaning the previous stage is giving you a valid output when you're being reset, right? Because that way you actually sample when the input to you is valid. Okay, so when you do these calculations, just keep in mind, indeed in that first phase, there really will be noise sampled onto that capacitor. Okay, and that noise is really just coming from the previous stage that's driving you. Okay? Actually, just as another reminder, even when you turn these switches off, you're also going to sample some noise. Okay, but usually the thing that confuses people more is what happens at the input right there. So when you start the homework, which again I strongly encourage you to do soon, keep this in mind because you're going to have to basically do this to actually get the right answer at the output. Because of course, once you've sampled that noise, when you go into the second phase, which again just looks like that, now you're going to take whatever that noise charge was and amplify it up to show up at the output, right? Okay, any last questions or? All right, great. So I'll see you guys next week.